In this video, I'm going to talk about strong interactions, or the strong force, and Quark confinement. This is part of topic 7.3 of the IB Physics Syllabus. That means it's relevant for both SL and HL physics. Please take a moment to read the success criteria for this video. So first of all, I want to point out the difference between talking about the strong interaction and the strong force. When it comes down to it, it's just if I want to talk about the force itself, that's one way. But if I want to talk about how it is caused and what's going on behind it, then I'm going to call it the strong interaction. In one of my other videos, I talk about how it needs an exchange particle for this to occur. For the strong force, it's a gluon. Now, talking about physics at the IB level, we are not talking about here at university level. So there are a few simplifications that we're going to talk about. And first of all, with the gluon being the cause of this nuclear force, we are not going to worry about its color. We are not going to talk about the color force or some of its other mediating particles. We are just going to refer to the gluon as being the exchange particle. And a little later on, when you start talking about using Feynman diagrams to show these interactions, a gluon is going to be shown as a curly line. So where does this occur? It's going to occur inside the nucleus, thus the name strong nuclear force. It's going to be what's going to hold our protons together and neutrons in the nucleus. It's also going to be inside the proton or inside our neutrons, holding the quarks together to create one particle. So let's think first of all what's happening inside our nucleus. So we've got protons and neutrons, and we know that those protons should actually be repelling each other. And they're very close together. Remember, if we had a football field being the size of an atom, the nucleus is only a ping pong ball in the very middle. And if that means those particles are so close together, we should be getting a huge amount of an electrostatic repulsion. So there must be something really strong, like the strong force, holding it together. So on this diagram here, I've got this red line showing me that as I get closer and closer together, the force of repulsion gets larger. And that's a 1 over r squared line. So we've got this other thing, this strong force. Now the exchange particle is the gluon, and it's kind of cool in the fact that it will interact with other hadrons, like the quarks, or the quarks inside the hadrons, but it actually will also interact with other gluons as well. So that's kind of cool. Our photons don't interact with each other. They zip on through and past one another without even noticing. The other thing is that it's really, really strong. You can see here there's a force of attraction, very strong. But if you go farther and farther out, there comes a point where it basically goes down to nothing. One of the videos I'm going to recommend in the description talks about how the strong force can kind of be thought of like a rubber band. When the quarks are inside the proton or the neutron or hadron, then there's not, they're allowed to move around inside that area. But once they start to get a little bit farther, they're really pulled back in tight. And if I get to a certain spot, that rubber band's just going to break. And in that case, it's too far from the strong force. And that's where we start to get unstable nuclei. If our nuclei was stable, then we'd have this force of repulsion equaling out our force of attraction here. And of course, then I would have no net force, and our particles would stay together in the nucleus. We can't have it always being attractive, because if you think about it that way, what's going to happen? Well, our protons and neutrons would then be overlapping each other and trying to occupy the same space. So if we get too far close together, we do have some repulsion. They can't be in the same spot. So let's look a little closer inside a hadron. So over here on the right, I've got some baryons, and I have some mesons. Remember, a baryon is made up of 3 quarks, and meson is made up of a quark and an antiquark. So how do these all stay together and create one hadron? Well, they're exchanging gluons back and forth. And again, remember I said we've got something called color. Now, where did this thing come up from, this idea of color? Well, when we talk about charges or poles or things like that, it's all black and white. We have one or the other. But in this case, this idea of color charge, there are three possibilities. And so we had to come up with something that we could talk about that just didn't have two options. So they talk about the color of a quark. We don't have to go into why we have to have a red, a green, and a blue quark all the time and how that keeps the hadron all together. One other thing I want to point out is you really should know a proton and a neutron and know what quarks make up those two. You don't have to know anything else. The IB is not going to expect you to memorize all the different particles in anything else. I do recommend to know that a kaon and a pion are both mesons, just because it's kind of nice to have an example to use in a question. Okay, so I have here a proton, two ups and a down quark, and we know that they're exchanging gluons back and forth, which means that they're being held all together in our proton. So let's think about this for a second. What if I take and I grab a hold of one of these quarks and I try and pull it out? Now, as you can imagine, if I'm going to try and overcome this strong force, I'm going to have to use a lot of energy. Now, that whole process of adding in energy, not only is it going to take a lot, but we've got this equation here, E equals mc squared. Now, you might have already done topic 7.1, or it might be coming up. This is the equation that a lot of people realize Einstein came up with. Now, this is not where he got his Nobel Prize for. That will come up in topic 12. But it's really important nonetheless. What we're talking about here and what he's pointing out is that energy and mass are actually two of the same thing. They're just different forms. Kind of like we have water and ice. They're both H2O, but they're in slightly different forms. So with his work with relativity, he came up with this idea that mass and energy are just two forms of the exact same thing. So if I'm pulling on this down quark and I pull it out and out and out, some of that energy that I'm going to be using actually is going to be transforming into creating two new quarks. Now notice I've been pulling on a down quark. A down quark is being created here and its antiparticle is right here. Remember I talked about pulling on that elastic band and eventually it's going to snap? Well, eventually what's going to happen here is I'm going to pull this out so far that this is now going to split along this dotted line. And when it snaps, I actually am not going to have that quark all by itself. In fact, you can see here I've got a meson and my proton hasn't changed at all. I still have it here. So this idea of quark confinement means you'll never actually have a quark all by itself. If you are going to put the energy in to try and pull it away, that energy is going to be so great that in fact it's going to transform and create two particles here that have a mass equal to that energy, and when it does break apart, I actually will have a meson. I will not have a lone quark. So quark confinement means you will never get a quark isolated by itself. So please take one more read through the success criteria, and I hope you can say yes to these 2 points.